Hello, everyone. So I have this hard task. Oh, I hope it's not too loud. I hope like the sound will be controlled. But I will do that all the time. Okay, I'm from Brazil. I'm very loud. I live in the US for a while. And I'm like really, really happy to be here. Like, it's not easy to have an audience that really you talk to and they are the experts in the field. So the talk really makes sense to that audience, to the entire audience, hopefully. I work in the CPU area in the field of like low-level security for a while now. I've been doing exploits and vulnerability research for 25 years, but the last 15 years I was actually doing CPUs and CPU bugs and CPU-related things. I started by accident. I was looking at SMM, system management mode. I read that like it was used by some other purpose. I started investigating which other purpose, and I ended up finding a CPU bug that I had no idea it was a CPU bug. And from there on, things just kept going. I currently work for L3 Harris, but like as a disclaimer, I'm not here like representing Harris. Like what they do doesn't really necessarily fit with sharing a lot of information on how to defend systems. Basically, another disclaimer that I want to give is that like I will talk a lot about the experiences, things that failed, things that did not went well, right? I will talk about failures. And like I will be like very frank and open when I talk about those. Like they are my perspectives, right? Like know that like I might be wrong in many of those, right? Like there's always multiple sides to a story. I can only show the sides that I know, right? Like there is way more to that, right? One other thing that like I want to say is that like nothing here is personal attacks, right? I omitted names, right? Like you see that I did my best to not identify the individuals, but sometimes I will talk about their positions and their companies. And the idea being just so you understand the power relation that existed at the time, right? Why those individuals could make those decisions. I think that also serves as a warning, right? Nobody will, never make mistakes. We all make mistakes. The best way to avoid those mistakes is to listen to the teams, to engage more people, right? Like, and when that engagement is prohibited, when that engagement is stopped with no data, there is likely something else that is going on. Maybe we just don't have the entire information, right? Maybe there is other concerns that are non-technical, but that's always, like a trigger. That is always something to be aware. Also, since I will talk bad about like certain things and certain behaviors, I will try to also praise good behavior and good companies and good folks doing the good work, right? Like, because I think that's also important, right? I will also try to do that to emphasize the importance of some research. Sometimes we do something, we publish, like maybe there's references, maybe there is media, maybe not. Like as a researcher, many times we just don't see the downstream impact this causes, right? How companies change internally because of some work. Maybe nobody even know that that work was that important. And that work drove like some major changes. That's changed the world. And that's in the end what we all want, right? Like we want to have that impact, want to do things that matter. So, as I said, right, like I like to describe myself as a failed farmer. So that's what I'm terrible at as well, right? But I'm terrible at many other things too, right? Like I found some like microarchitectural bugs. So this is a list of a few of those that got credited, right? Like the ones in black are side channels. You will notice that there are many that are not in black. The majority are not in black. So side channels got this overwhelming view of the media, but side channels were not the overwhelming majority of the bugs, right? And that's something interesting, and I will talk a little bit about some of that, right? But like nothing really means anything, right? Like doesn't matter what I did or didn't do. What matters is what I'm telling you, if you agree or not. And you are individuals, so make that conclusion by yourself, right? What I really recommend is look at the nuances. I tend to have way more information in these slides than I speak to. I have way more things that I write than that I really try to explain. And I add references that sometimes add way more context to things. So use those, like before judging anything that happens. But besides all that, right, besides finding bugs and having failed as a farmer, I am a failure. Because really, at some point in time, in 2017, I accepted the challenge to solve side channels, right? If it was important or not, if it was overhyped or not, I took the responsibility. I believed I could do it. I believed I could put a team to do it. And I really believed I would do it. And the problem is not solved. Therefore, I failed. So most of this talk is also about that failure. I will actually share things that went wrong, as I said, right? Like some of those things are political. They have nothing to do with technical, but nonetheless, I was there. I was in the position to try to make the change, and I couldn't, right? So they are failures on me. And hopefully, you won't make the same failures. You will manage to avoid some of those traps, or you manage to avoid, your companies getting to those traps. That's kind of like the idea of sharing. But I will not talk about my farming failure. Just understand that I had 14 alpacas and they all died at some point. So, also, I think that for me, this talk is really important because it's the first and the only time that I will be speaking about microarchitectural bugs in public. Right? Like I never did since the issues started, and I will not do it again. I am done with it. I'm passing the ball. I hope better people than I can now solve the problems. I will work on the problems from a different angle from now on. And at least for a foreseeable future, right? Like we never know, later what will happen. But some things are really bad. You will see, it's terrible. It reminds you on the 90s, 2000s, when vendors had no clue what they were doing, and the first reaction they had was to threaten you. But also, I hope I will share some ideas on how others can do better, and how you avoid some of those threats. And hopefully you also notice that a lot of those issues are actually super simple. People doing exploits for Windows, mobile devices, they are doing really, really hard stuff, right? Like a lot of the side channels, a lot of the microarchitecture issues, they are really simple. It's just a matter of there is not a lot of documentation yet. There's not a lot of understanding. There's a lot of assumptions that the vendors do better than they actually do. But when you actually look at the issues, they are not that complicated. So it's not that they are not getting fixed because they are complicated. They are not getting fixed just because there's not enough minds looking at it and working. So I also believe a lot in transparency and openness. I fought a lot for it, right? I really did. In many occasions in my career, I had situations where I challenged the status quo of the industry or of individuals in the companies. So I will keep trying to do it, right? And one hard truth for me is that side channels are overhyped. I honestly did not want to do it when they started. I did not want to do it at Intel. At some point, I literally asked it to leave it. Then I moved to AWS saying that I would not do it, and I ended up having to do it again. And then I went to Google with the guarantee I would not need to do it, and again I had to do it. So it's unfortunate, true, that somehow when people show me a problem and I believe I can help them fix it, and I see them making a mistake on the problem, I have this thing, right? That's probably what brought me to give this talk, right? I could just have said no, but I end up coming here and trying to, maybe now I will make a difference, right? So it's a hard truth, but it is something that I do. And again, I want the researchers to understand the impact they have. I will share some that, I think people did not realize the importance of the work. I will start saying also that, I have, really, a different angle or a different way that I look at security, right? For me, security has two main challenges, and that's pretty much it. Even though, of course, those challenges are big, right? One is assumptions. So literally, we assume things, right? And those assumptions, they're necessary, right? Systems are way too complicated. A friend of mine and I, we always joke that nobody really knows how a CPU actually boots. Nobody knows. Nobody at Intel, nobody in the world, all these interview questions, BS. There is nothing. Nobody really knows, right? There's so many things that go on that a power on is really people throwing the dice. So you have 2,000 engineers working on a project, and then it comes to the day, they throw the dice, and everybody's unaware if it will actually boot. And it does boot, and then the humans go and do a lot of cool things with those devices that are complicated. And of course, that's the same for many other things that us humans do, right? It's complexity, we abstract them, and we build things on top of it. But there's a lot of assumptions for that to work. That's how we remove complexity, right? We create an abstraction layer, and that abstraction layer makes assumptions, and those assumptions are simplifications. Otherwise, we would not be removing complexity. And that's where a lot of security bugs exist. Because we assume the wrong things. Also, a lot of those assumptions, they are made without thinking about an adversary. Someone that is interested in breaking the assumptions. Right? And that's really, an important element. And then there is composition. Composition is part also of the assumptions. As I said, it's the abstraction means like you're composing things. But it's more than that. I think, while we all empirically know, and many know in the theory, and many try to apply it in practice, if a system A is secure and a system B is secure, the composite system between A and B is not necessarily secure. I think we all know it, but it's still, when we actually doing the work, we make the mistake of making that assumption that that composed system is secure. And again, failures come and continue coming, right? Like, look at the computer, right? Like, you have devices. We always assume that those devices cannot be compromised. I will give an example of a CSME. CSME got compromised. Intel keys end up not being necessary to unlock the CPU. Now people can do microcode research. So a lot of assumptions were broken just because we forgot the composition or we ignored it for some reason or another. One more item that I forgot to say is that, because of that, I also believe that, when we look at a system and we look at the design of a system, somehow we can imagine already the bugs that that system will have. For me, this is, this idea, I always had that gut feeling that that was true, right? Like that, what you learn from bugs in one system apply to bugs in another and so on. But over time, I started maturing that idea, and Sergey Bratus really, helped me putting the theory behind it. That really, it is a fact that you get a researcher that worked and found a lot of bugs in a given complex system, and you put that same researcher to work in another one, and somehow that researcher still succeeds, right? They will still find those bugs because that experience still counts. So use that fact, right? Don't be afraid of going after other targets. Whatever you learn, it doesn't matter what is the system. That feeling, that gut feeling on how things fail, how you approach those systems, it will apply, right? And we will have, in this conference, examples of researchers looking at other areas and finding that. Also, I think, when you're approaching a complex system, for me, right, there is only 3 things you need to do. Again, because it's simple doesn't mean it's easy, right? But I think, you have to have 3 questions, right? The things that you don't know, but you should know, right? So, for example, I'm reading some definition. Whatever is the definition of the given system, I'm auditing. Some are way more complicated, way more detailed. Some are have no details at all. But every time you're reading about that, you start thinking about the things that you need to know about that system. Let's say that the system says they're saving data on the disk. Do you know if the data is encrypted or not? Do you know if the disk is a hard drive, SSD? Is there even a difference? Is it by flash? What is it? Right? You have questions. It's natural. You're reading something. You need to be curious about that something. And any questions that you cannot answer about the system, you should be able to answer. Because knowing the system is what makes you finding bugs on that system, right? Because that's when you start thinking about the behavior that was not supposed to be there, but it is there, right? It's really those unexpected things. Also, there's things that you should be able to do, but, if you're not, it's time to invest in your tooling, in your capabilities of, analyzing that system. So this is a very good example in hardware, because a lot of times we go and try to look at something on the system, and we're like, well, the documentation doesn't really say if it's encrypted. I believe it is. I can see some of the data looks like encrypted, but I can't really poke into the communication. Why not? And the interesting thing is, just by doing it, you start finding bugs. Bugs, they show themselves, right? Because it's natural. You're learning about the system, and all those things that nobody did, because if there is no capability to do that work, if there is no way, if that capability doesn't exist, it means nobody really tested it. So everybody's assuming it works by the definition, whatever definition they created. But really, it's just an assumption, right? We don't really. And then, what is the taxonomy of past issues? Because every time you're looking at something, there is a past. Doesn't matter if it's a really new thing. There is a past that is related. Either a technology that this is founded from, where the idea came, similar systems. But somehow there is some past that you can leverage to try to have an idea of the issues that this system has. Some of those are just functional. They were not even classified as security issues. It's unbelievable the number of functional issues, literally, that appear that in the end have security implications, but nobody really noticed. And that's also a good reason for looking at the record. Also, I think, if you are the designer, right, if you are in the hardware side and you are really trying to design a system, survivability is highly important. If you're attacking a system, survivability is super interesting as well. Because whatever the system cannot patch is the bugs that really, really are worth it. Right? Think about it. Is the bug that will stay there. Is the bug that, you know, like there will be, maybe there will be workarounds, but there is a high chance that that bug will last. Right? So it doesn't matter if you're trying to secure that system or if you're just trying to break it and keep like access to a given system. Survivability is crucial. And I will show you how survivability fails, right? Like how companies are blaming their customers for mistakes, like Intel recently did for OEM. And then, like, in the end, it's just a mistake of Intel's teams looking at the survivability of what they do. So I will give some examples of those. But really, you know, like, I think what everybody wants here is the meat, right? Hey, what did you leave? Where is it? What went wrong, right? Like, so I omitted the picture of the meat. So if you want, you can imagine an ice cream, okay? It's totally fine. I don't mind. I don't judge. I do eat meat, though. So the timeline for the side channels specifically, and this is a completely made-up timeline. It's no academic, no scientific. It's all coming from my mind with a little bit googly. But sometime in 2007, not 17, okay? So to be very clear, there was a paper. And that paper was interesting because they talked about predicting secrets via branch prediction. And it was an interesting paper, you know, like a little bit more academic work, but, you know, like a interesting paper. That paper per se did not necessarily make the news. That paper per se did not really got a lot of impact. But because that paper happened, there was an action that became, you know, like the beginning of, you know, like the mistakes around sidechain. A senior principal engineer from Intel, in that week that the paper came out, was going to a university, Oregon State University in Intel. There's a lot of collaboration there, to give a talk. And that talk was about microarchitecture, had nothing to do with security. The guy was a designer, had nothing to do with security. He was literally teaching engineers how to actually look at microarchitecture, how to do RTL properly, and so forth. But there was a paper that came out. And the paper made some strides. There was some news at the time. So he knew he would go to give a talk to university students, and someone would challenge him, right? Someone would go and say, yeah, you know, but it's broken because there is this side channel thing, right? So he had to be ready. He had to have an answer. He knew it was going to come the question. So his answer was actually really, really super well thought, in my opinion. Basically, he said that the cache line boundary, so any challenge, any side channel from software, that leaks something, but it's basically in the cache line boundary. So it's the entire cache line that needs to be linked. It's not like intra-cache line, is a software problem. He made that statement as an answer to students. It was not a statement that was vetted by Intel Security. It was not a statement that actually went for a lot of discussions or anything. It was just a talk to students. As things go, that talk, of course, the slides were shared internally in Intel. And it's a senior principal engineer, so it's a guy that has power, that's known, that people respect, right? That idea that was just supposed to be, hey, so students let it go and you can focus on your talk, became a rule. Over the years, the rule grew, and you guys all played, and girls all played like this phone game, right, when you were kids. What happens when you give an information on the phone and then you let the person pass, and the information gets in the end of the line? It's a completely different one. And as it goes, when I joined Intel in 2013, you know, basically the myth was just, hey, side channels are a software problem. The detail of the cache line boundary even disappeared. And more than that, it was a rule. Like security teams assumed it as a rule. It's not that nobody looked at side channels at all. There were, in Intel, you have a lot of people that are researchers, they have things with the academia, they're smart folks, they're interested in topics. So people from Intel, they did look at it, right? But as a rule, as something that the company cares about, side channels was a no-go. If you go to management and say, hey, you know, I want to do and look into side channels in this area, in this new feature. Why? Side channels are a software problem. We are a CPU manufacturer, we are not software. Right? So look into how interesting. Something that was innocuous became the rule. And the company paid billions of dollars later, right? Like as we know. 2016 though, so 3 years after I joined it, there was a talk in Black Hat And basically it was DRK. So they used the TSX to bypass KSLR. So another secret is I hate KSLR. Okay, I never believed it's a good idea. I think like the investments are completely wrong on the technology. I think like the kernel is very complicated, and if you want to do it, you need then to do it properly and invest in removing all the info leaks and all the bypasses. Otherwise, it's something that you're just wasting money. You just keep putting things and and it doesn't really give you the benefit that you should have. So when I saw that talk in Black Hat, my first thought was, hey, I will finally convince Intel to say officially that KSLR is not supported. Literally, I am admitting I'm selfish, right? I had this interest in mind. So I knew that the open source team in Intel was investing a lot in KSLR patches to the Linux kernel, and I hated all of those patches. I really did not want those patches to go. So I basically started a discussion inside Intel, saying, hey, there is this vulnerability. Folks are using our feature, it's a CPU feature, CPU capability, to bypass KSLR. Our software side of the house invests in KSLR. But our hardware side of the house is saying we are not going to fix. Right? So which one is which? Right? Either it is a bug and we need to fix, or it's not a bug and we need to stop investing in KSLR because it's dead. Look into how interesting it is when you are selfish, right? Like you can leverage things in an interesting way, right? Obviously, that doesn't really make me many friends, right? But I still have fun. So the matter is, I started this discussion, and the discussion became serious, right? Like, because, of course, a lot of people also believe that KSLR was not the best investment, at least on the way that it was done. Some folks tried to, okay, then we doubled investments in KSLR and made it proper. Good, doesn't matter. The important thing is, like, let's have the discussion, right? But that was, like, really the first time that, folks started seriously looking at side channels as something that made a difference. Because now we're talking about we are investing money in something, and we're saying that we are not going to fix. We don't treat it as a security boundary. So what is that, right? Then in 2017 came another paper. And that paper had even more impact. And again, was a paper that not a lot of people, consider. So it was called ASLR cache. So that paper, the researchers actually used B2B collisions to actually try to bypass the ASLR on Chrome. And the interesting thing about that paper, and that's what really caught my attention, was because that's Chrome, and that's ASLR. Chrome is a really rich target. A lot of folks want to write exploits for Chrome, right? Like a lot of people use it. It's very hard. It has a lot of mitigations. And ASLR is a mitigation that really matters. KSLR, everybody always had bypasses for it. But ASLR is different. You need bugs for it. And now, if a side channel can basically save you from having an additional bug in your chain just because the side channel will give you a bypass, that's major. As it happens, right, the research results were not as necessarily good as they were presented, but the research and nonetheless was important and had results, right? When I saw this, there was another thing. I knew actual exploit writers, folks doing it, would actually look at side channels. It was obvious, right? Because now they can save money, right? Like they can, not have to look for info leaks anymore. Imagine hey, the CPUs are gonna give you the ASLR bypass for free. So I knew way more heavy hitters would look. And I knew that Intel was not looking, right? So we were behind. We are definitely not aware of what could come, right? This idea did not come from us at the time, right? So what I did was I started talking to everyone in Intel saying, hey, heavy hitters are coming. We better be ready. We better get into the state of the art. Let's do it. And management said, yes, let's do it. It makes sense. You convinced enough people. There was enough technical folks that agreed it was important. So we get the go-ahead to start ramping on the topic. But then, again, appears a super fellow. The fellow is like this super brain, right? So the fellow that was responsible for security decided that there was no ROI in doing it. He was releasing a feature that, by the way, was dead 1 year after it was released, called FPX. I will make fun out of that feature again later. But he was releasing that feature, and he wanted my team to, instead of focusing on the side channel things, hey, go look at that feature. He even put a meeting with me to say, hey, it will be really better for your career if you look at the feature instead of side channels. Right? After all, Side channels, yes, you might find bugs, but who cares? Features are what gets you promoted, right? So, good. That, of course, it did not last long, right? Like 6 months later, right? Jan Horn from Project Zero ended up sending the infamous report to Intel. Like, hey, folks, I observed those things here. There's just observations. There's 3 cases here that I see. One completely, bypasses, eBPF and other, container protection. So that was the V1 using, direct. Then, the second one was, hey, completely bypassing, gas isolation. So leaking from the hypervisor, leaking from other gas, which is also, probably not a good idea. And then the third one was meltdown, right? So literally breaking and leaking from the kernel. So essentially he was like, yeah, I found those things. I don't know if they're relevant. You guys probably understand a little bit more. But he broke all the security boundaries, right, of the CPUs. And of course, this was terrible. Immediately we had to react, right? The truth is we had to do something. After analyzing it, the report was really well written, right? It was hard to reproduce the exploits themselves. But the report was really well written. So I immediately basically raised the flag to the manager and say, hey, this is a new class of issues. And that's funny because I was told that I cannot use that term. You cannot say that something is a new class of issues, even if it's a new class of issues, right? But anyhow, a month later, Anders Fogg, which later came to work for Intel as well, I was glad that I managed to bring him to Intel, published a blog post about negative results. I almost had a heart attack when I saw his blog post. Literally, we had 1 month in, we're still ramping on what side channels really are. As I said, we were not very good at it. We didn't really have anything. But, he published a blog post. I was like, crap, he 0-dayed us, right? And now we have a problem. But interestingly, his blog post was about failed results. He literally made some mistake. His intuition was right. Everything was right. Even the POC looks proper. But somehow it did not work. Maybe there was too much noise on the system he tested. Who knows, right? Maybe he did not sleep well and solve zeros instead of ones. Who knows? Lucky, whatever. But the matter is his blog post basically said negative results. Which, in a way, we were discussing internally, hey, will that now mean that nobody else will look because he looked and failed? Or will that now attract even more people to try to prove him wrong? Right? And you have all this unknown. Will other folks try to test in other systems and end up finding whatever was wrong? So we were super scared. Then of course it did inspire others. Right? So for the rest of 2017, it was a nightmare. Because we started pushing patches to the kernel. For one of the issues, Meltdown, the solution was fairly easy to do in software. So patches started getting pushed to the Linux kernel. And Linus Torvalds, who was always very, adamant against this idea of splitting user space and kernel space since the 2.2 when the kernel changed that. Linus Torvalds said, hey, we are never going to do it again. He was adamant. And suddenly he was accepting the patches without really complaining at all, right? There was no comical jokes. There was no, tantrums, nothing. So others were like, well, wait a minute. There is this post that says failed. But now Intel is sending patches to the kernel, fixing something, and Linus Torvalds is way too accepting. So they started looking at it, and of course then we start getting reports from all the universities that were paying attention, right? So then obviously in 2018 the issues became public. And it was interesting because there was a big problem there as well. I don't know if many people followed, but AMD released the issues by mistake 1 week before the date. They sent a patch to the Linux kernel, and in the patch, they literally spoke about the security issues. So they literally made it public 1 week before the timeline. And that basically got everybody not ready, which maybe was a mistake on our readiness, right? We should have assumed issues could be public at any point. But anyhow, people were not ready. So Intel CEO was not aware, right? Which is a problem because he was interviewed. Other groups and many people were not informed yet inside Intel, which became a big internal political problem. That political problem culminated with our CEO saying there was hardware fix coming when they were not, and then hardware fix needed to be created, otherwise he would be a liar, right? Which per se was a problem, right? You can imagine. But also, you know, like Intel ended up like having to create this new division to show that they were like really reacting. The division had 6 VPs, so executive VP, senior VP, VP reporting to VPs, but no engineers. So we called the army with generals, right? Like they even had, you know, the marshal or whatever is the name of the hire, but you know, like they just lacked the engineers to actually do the work, right? Of course, they ended up getting the engineers from all the other groups. We ended up reporting to those VPs. Interesting times. But also, there was something that was interesting that, you know, like not a lot of people gave attention. But there was class action lawsuits against Intel. 2 major ones. One in Israel, one in the US. And that changes everything because now legal gets involved. So just so everybody understands, it got into a point that every email I sent, I had to first send to legal. Legal would review the email, for then I am able to send the email. For my team members, for management, for others in other teams. So the orientation is, of course, now you work all together. So it culminated with, hey, if you are a journalist, just observe the parking lots in holidays and stuff in companies, and you know if something bad is happening because security folks are going to be parked there, right? And that's exactly what happened. We were there in Christmas, we were there in New Year's. You know, like I postponed my honeymoon. We literally were there, right? Like we had this small collaboration room where then, like we sat all together, and that's then, like computers everywhere, then, like completely not up to code. It's interesting how fire rules and all these other things that companies say are so important, they are irrelevant when things matter. But the truth is, like, why really me and my team, right? Like the truth is, you know, like yes, we were the client's team, right? Like we were covering CPU clients, so then like it just made sense that then, like it goes to us. Really, you know, like I only had a team because of a lot of good people that really helped me in my career in Intel, and I wanted to put kudos to all of them, right? Like, because they really helped me either sharing, you know, like really helping me understand, saving me from problems, right? Like, and without those folks, you know, like nothing that I did would ever be possible. I would not even manage to ramp up, right? It's way too complicated tech, way too many things to do, and I don't know, like I really wanted to add the kudos. But really, the elephant in the room, the thing that nobody wants to acknowledge, right? And I would love to say that, hey, I was the best person for the work. But the truth is, really, there was another story that one did not, you know, like get the attention when everybody was looking at the side channels. And it happened even before. And it's interesting because the impacts of that story still are felt today. Literally, past week, there was a talk in OffensiveCon by Piotr and team. And basically, this talk uses this research, this vulnerability that was found by the positive technology folks. They reported this bug to Intel. The bug affected CSME, and essentially it gave code execution in CSME. And the interesting thing about this bug is not really the bug, it's really the response. What happened is, like, at the time, you know, like, Intel looked at the reports, and it's like the way that the Intel PCert worked, I don't know if it's still like that, but basically the PCert gets the report sent to the team that is the product team that is affected. So they sent to the CSME security team. It's a very good, competent team. And those guys looked at it, looked at the bug, and basically said, hey, this bug is not exploitable because we have canary protection. That's it. They just said, go away. And the positive technologies guys, they basically got that response and told Intel, well, you know, we wrote a full exploit, you know, look, there is a loop, there are main copies inside a loop, you overwrite, you get control of the execution before it returns. I don't think you were right saying that the canary protection even matters. We didn't even notice it was there. And, you know, like, of course, you know, like that's how life goes, right? Like, positive technology was basically telling Intel that they had an exploit, but they would not share. And Intel was saying, hey, without an exploit, go away. And then, like, lucky, I knew the folks from Positive Technologies. I've been in the conferences in Russia multiple times, right? It's unfortunate that I can't go anymore. But the truth is, I knew those folks. So they reached out to me. And they basically said, hey, Rodrigo, we know it's not your area, right? You're doing the CPU things. But, you know, we have this bug. We have the exploit. Intel is saying no. We will just full disclosure. I was like, well, that doesn't really sound right, right? So I asked the guys, hey, you know, can you share images? Because I literally had no way to even access the images. You know, like, again, you know, the things that you should have access, but you don't. But, you know, like, I was in another team. I understand that there's separation. But, you know, like, essentially, you know, like, they actually sent me the images that they were actually analyzing. They were so nice that they sent the notes, they sent pictures. Oh, hey, this is the layout of the memory. This is where the corruption works. So it was trivial to reproduce their work and write an exploit for it. And management did list them. Management was like, well, there is something going on. Before this vulnerability, there was also another vulnerability that affected Intel AMT that happened in the same year. And this vulnerability was like a web authentication bypass, a trivial bug. So folks were like, well, there is something wrong with that team. So literally, Intel respawned everything and it started re-looking at the security of the CSME. As I say, the team is super competent. They were just overwhelmed. They were just badly organized. And we managed to modify that. Folks started getting the visibility they deserved. They started getting the promotions that they deserved. They had the time to actually look at the security of the components. And they finally, started making the difference. And you can see that this culminated in good results because since then, there is no CSME bugs happening, right? All the research going since that time is basically continuing and leveraging the same bug, right? Which is great. Changed a lot of things, but that's an example of an impact. That research not only let now us reverse engineer microcode, which was demonstrated in offensive past year, but it also changed an entire group inside Intel. The career of many folks. It's like a huge impact overall in the security of the industry. So it's really, really good result from research. But then why I criticize Intel and AMD so much? So far the examples were great, right? Intel did change things. The mistakes happen, we change and we improve. But that's more timelines missing. As I said, I'm terrible constructing the timelines, right? But some point in 2018, when the issues became public, AMD did a marketing campaign saying they were not affected by the issues. Even though during 2017, all the time AMD was saying they were, and they were telling Intel that they would actually apply the mitigations that Intel was sharing with them. So suddenly, when the issues became public, AMD said they were not affected. It was so bad that they actually put a banner in the airports in California saying, hey, use AMD, we are the only ones not affected, so trust your vendor, right? Confidential computing. So at that point, Intel high management, of course, needed to involve legal. Legal, of course, wants to open a lawsuit, but you cannot open a lawsuit if maybe they are not really affected. So somebody needs to prove they are. So we were asked to look at AMD, and of course, I have a really big ethical concern, right? Because you are the big vendor. Right? You are the major vendor. You have all the resources. You are 10 times bigger than your competitor. Is it normal that you get your team that is working on those problems and put that team to work on your competitor technologies? So I challenged management saying, hey, I don't agree with doing it unless we agree and have the commitment that we're going to share every single thing we find to AMD, and that's not going to be used as marketing or anything else other than the lawsuit, which makes sense because the lawsuit needs to happen. They did the wrong thing. And sharing with them. And management agreed with that. And they actually did it. It passed many years. Some of the issues are still getting rediscovered now, right? Some of the issues were not fixed. Some of the issues, got silently fixed. Some of the issues were partially fixed. But basically, I also want to say kudos to IOActive and Binary, right? For actually going and poking. There's gonna be talks from both, because the truth is, we need more people poking, right? As I said, some of those issues found 3-4 years ago, they still not fixed. But there is more, right? Unfortunately, and that's the unexpected downstream impacts. AMD ended up replacing the head of PCERT. And they now have somebody that instead of trying to collaborate, it's even worse, right? There is threats. You report something, they threat you, they escalate. They don't tell you the truth. They dismiss the thing, and then later they try to do something on the side. And that's becoming worse and worse, and it's becoming really the characteristic of AMD's and Intel's PCERT. In the past, just so you understand, I reported bugs to AMD as a vendor, and the AMD came to me and they were like, hey, we don't know what to do. Cisco Talos is killing us finding bugs in drivers in our graphics stack. Can you help us? And I helped them set up basic fuzzing environment so they could find the bugs before and fix them before Cisco Talos were finding them. right? But they were open, right? Like the problem is not doing it or not knowing. The problem is like when you lie that you do or you know, right? So this completely changed it. Basically, there is a lot of marketing and legal driving PCERT. So you guys have an idea of the dimension. Intel's PCERT has a marketing analysis or marketing intelligence team associated to it. So they literally look at, hey, this research tweeted, or this guy gave this talk, and they look at the trends. And if the trends are dying down, they say, hey, we don't care. If the trends are picking up, if people are retweeting, if there is engagement, oh, wow, this one we need to act. So it's literally marketing-driven response. Not anymore technical-driven, not anymore real collaboration, right? And that's something that I cannot, abide and agree with. And there are many anecdotal evidence to that, right? So I shared a few, so Plunder Vote, there was a collision by different researchers, different than the usual advisors. In this one, they never said SMM and hypervisor were affected, even though they were. Later on, herd split came with very similar kind of work, very similar kind of a vulnerability. Again, no mention on SMM and hypervisor, but I did see that the hypervisor was affected. Specifically, I saw that Zen was exposing the MSR and the bug was exploitable from the guests. So I sent an email to Intel PCERT saying, hey, folks, Zen is also affected. You probably should look at it because a lot of folks will not notice. Your advisor don't mention it at all. And then the PCERT VP, the VP, look at that. I'm so good that I got the VP to send an email to tell my employer, in another group of my employer, another VP, because of course that VP only talks to VP, right? Rule. So the VP sent an email to my employer say, hey, your security team is trying to blame Intel because you made a mistake. Zen is a private hypervisor. It's crazy because the person didn't even know that Zen is open source hypervisor that Intel actually commits code to. So it's kind of crazy. And they try to say, and it was just an example, we did not really care about the Zen case. But I promise you that this is not complicated, right? I promise you that the bugs are simple. So let's start looking at some simple ones, right? There was the reverse BTB poisoning research. It was done by a Brazilian guy, José Luiz. And the research itself is complicated, okay, just to be clear. But, he reported to Intel, and I will share the slides of the response because they are hilarious. But, it caught my attention when it became public because his idea was hey, instead of trying to attack the victim by controlling the branches that the victim use, and therefore making the victim execute gadgets that you are interested in, what we want is to see the branches that the victim used and use that information as, a bypass for ASLR. Not very different than, the ASLR cache and other work, but, he basically built on that. And, the interesting thing is because there was a mitigation that is the IBPB, which flushes those buffers, right? So if the mitigation is applied between both sides of the communication, there is no bug. But if you think about, the rationale for flushing was the attacker controlling the victim. So that flow, you need an IBPB. From the victim back to the attacker, you did not need an IBPB. So it's an optimization that makes sense. So the threat model is different. Even though the same mitigation works, it is a very different, flow. And of course, you need to look at how people are implementing and if anybody optimized. But Intel completely dismissed. So he basically presented, right? He was well, if it's not interesting, present. So I reached out. And of course, Brazilians, we speak Portuguese, we eat meat, and we drink a lot. So we end up coming up with other ideas of how to expand the targets. And we end up saying, hey, yes, we can use, instead of the indirect branches, we can, that you were using, we can use rats, which is a kind of indirect branch, but it's more common. And we end up doing a write-up that, as usual, we just shared with the vendors. So all that is a little bit complicated. You need a little bit context, right? But the vendors, of course, as usual, they said, yeah, fuck off, right? Nothing here. But, it just happened that, we during the POC, when the POC that we had was showing signs, even when the mitigation was used. And, we could see some signal. Something was leaking. We were not sure what. But because the vendors told us that, hey, there was nothing, we kind of well, we're really bad. Our POC is broken somehow. Let's have a look. What is wrong? Why are we seeing it? And it just happened that actually the kernel mitigation was broken for 4 years. And if anybody from the research that we reported just ran the POC, they would have seen it. But they didn't. And even worse, the POC is almost a Spectre V2, as is from 2017, June, when Century Intel, 2018, January, when they became public. The same POC, you just needed to actually go and run on a Linux system, activate the mitigation, and you would see that it was still leaking. They broke it, and none of those vendors, none of the big companies saw that the mitigation was broken. Right? So, where are the basic tests? Just run the POC. Like, literally. Right? Cool. Then there was another one that was actually even more hilarious, right? Because we for the rat bleed issue, AMD wanted to do a solution called Jump to Rat. And, my gut feeling was that solution was really bad. It was a really bad idea. Right? Like, it was using a directive in the mitigation itself. It was trying to do some kind of polymorphic code. I thought that it looked really ugly and it needed to be bad. So I was like, okay, let's prove it's bad. So we started looking at can we actually make the window bigger? There was a research that my team at Intel released a few years before that proves that you can, but we wanted to do it with rats, so we started looking at how rats really speculate. There was a lot of misunderstanding on that, so we did a write-up. And as usual, we sent the write-up to the vendors, and as usual, the vendors really fast basically said, hey, there is nothing here, right? Like, it's, oh no, you guys know nothing, right? But they still asked for 90 days embargo. Google, as a great company, right? Like, they were like, yeah, let's give them 90 days. What does it matter? We just wait a little bit more. When the 90 days passed and we published, AMD sent a mail threatening legal action and requiring us to remove a sentence from the write-up and basically, demanding an apology. That apology became famous in some circles in Google that were involved on it because I said I would not apologize for their mistake. They had the write-up. They should have read it. Yes, I did not make a big deal of that sentence. The sentence basically said that the flush of AMD did not flush their RSP. They call RAS. But the flush did not do flushing, which is kind of interesting, right? Hey, it's a flush. But I noticed, and I mentioned it on the paper, but I honestly thought that everybody knew that their stuff did not do the flush of the RSP. And I really believed that everybody was using Ratpoline, but it happened that Microsoft was not. So it just happened that we zero-dayed Microsoft by accident, and Microsoft was upset with AMD, AMD was upset with Google, Google was upset with me, and I said I would not apologize. So my boss, the VP, and all that, we had a meeting, and they're like, okay, everybody's signing. You don't need to worry. We will let you read what you're signing. And I was like, well, everybody's signing, but I am not. So it became the letter that everyone signed except Rodrigo, the problem person first. So, and this is really a gang problem, right? They even call it the gang of 20, right? It's the folks that were put together to discuss side channels. They receive the information in the companies, so they are the ones that decide the fate of the world, and they are not very good, right? And they will come after researchers. There's many examples. Ratpoline was one example. Everything was broken there. We made sure that people understood it was broken. People ignored. And then when I was with Google, I was like, hey, did you know that there's this, and this problems with Ratpoline? And we're like, oh yeah, it's all fine. There are tickets. So I was like, well, let me check if the tickets are done, right? Did somebody perform the tickets? So they forgot to stuff their RSB in the SMI handlers. They forgot the microcode patch. Literally, they were not patching the fleet. Interesting. They forgot to fill the RSB coding on the kernel. It's an interruptible code. They forgot everything. But they knew. And there were tickets. So trust them. Don't worry. ERBRS, the same thing, right? Intel knew, the problem. Some of them we even spoke openly. And then I still, folks let the technology get released. Folks still implemented. Hyperbleed was another work that, we did, which was literally, we decided to run after the problem with rats to ASLR, that the basic mitigation did not work. We're like, okay, what if we run the POC as is in the cloud? So we ran in all the cloud providers. And it just happened that all the cloud providers, no exception, DigitalOcean was the exception, but all the other cloud providers, Azure, AWS, Google had some weird behavior. And, in this weird behavior, it just happened that, it was a kernel bug that, it was related to EIBRS and their misunderstanding of how EIBRS works. And literally, it was just that, the SMT case for user mode was never enabled because they thought that the EIBRS would take care of that, and it does not. So basically, all the cloud providers, the basic mitigation, broken. Broken. Nobody ran the tests. And I bet researchers ran the POCs on those. They probably saw the signs, but they were maybe concerned. Maybe they assumed that things would work. So we got the interrupt. These are the slides just from Intel, just so you guys know. But we got the interrupt. They evaluated the paper. There is nothing there. And then they ask for the paper when the paper goes public for some reason. And then, of course, they recall the email. As if that deletes from us as well, right? So there's many other cases I try to share. I just want to say that, share information, get the slides I will publish. There's more cases here for you guys to laugh. The future is the rise of computational computing. We can't avoid that, right? Don't be afraid of challenging the status quo. There is a great actually talk in this conference about that. So look at that talk. I really, really believe those guys are doing the right work and they're looking at the problems right. And catch me up. Any questions will be for later, but I will be here. Thank you, folks.